The beauty of having an orthogonal basis rather than a traditional basis is that for each vector in the vector space, we can determine the coefficients in the linear expansion according to that basis. So we're able to find, if we've got y is equal to a linear combination of u's, where u's are our basis elements, what we found is that if our u sub i's are all orthogonal to each other, then it's very easy to find what those coefficients are for each particular y value that we have. And remember, we found that y, the coefficients are equal to y dot u sub j over u sub j dot u sub j. So it's of interest to us to be able to find an orthogonal basis for every vector space that we have. And the Gram-Schmidt process is a process that does that for us. Given the basis, we can we can turn it into an orthogonal basis, and it just makes it more efficient and easier to work with, whatever our purposes are. Okay, so it looks a little complicated. Basically, always if you're finding orthogonal basis, your first vector, you just fix the first, pick one of your basis vectors and fix that to be the first vector in your orthogonal basis. And then the second one turns out to be you're basically building a projection off of the first one. Okay, so we're going to take a vector or a vector space W where it is spanned by the linearly independent vectors 0, 4, 2, and 5, 6, negative 7. Okay, so obviously this is a subspace of R3, and we've got a basis for R3 out of these two vectors, but they're not orthogonal. So the Gram-Schmidt process allows us to construct an orthogonal basis. And, okay, so first step is we're going to let our V sub 1 equal the very first one. Alright, so this is we're going to call this x1 and x2. Alright, so our V sub 1 is given by 0, 4, 2. And our V sub 2, we're going to find as our x sub 2 minus our projection here, x2 dot v1 over v1 dot v1 times v1. Alright, so we get our x2, which is 5, 6, negative 7, and then we're going to do the projection of x2 onto our v1 or x1. Now notice x2 dot v1 is just equal to 0 plus 24 minus 14, so that's 10, and then v1 dot v1 is equal to, think about 0 squared plus 16 squared, plus 4 squared plus 2 squared is 20. So we get 10 over 20, or 1/2 our V1, and our V1 is 0, 4, 2. Alright, so we just get 5, 6, negative 7 minus half of that, which would be 0, 2, 1, and that is 5, 4, negative 8. Okay, so that gives us a orthogonal basis of 0, 4, 2, 5, 4, -8, and you can multiply or find the dot product there and see that it is indeed orthogonal. Now, in our projection that we did earlier, so we're finding the projection of x2 onto x1, and you can see that this first vector is orthogonal to x. This is our orthogonal, and then this is our projection of x1. Oh, I'm sorry, this one is our orthogonal to x1. And okay, so now if we want to turn that into an orthonormal, then basically we just take each of these guys and normalize them. So to turn it into an orthonormal basis, we just take each of those guys and normalize them. So for the first one, the length would be, let's see, square root of 20. So we would get 0 and then 4 over the square root of 20 and 2 over the square root of 20. And if you take the length of that, you'll see that it has length 1. 0 squared plus 4 over root 20 is 16/20ths, plus 2 over root 20 squared is 4/20ths. So 16/20ths plus 4/20ths is 1. And then to normalize this one, we see that its length is the square root of 25 plus 16 plus 64. So 25 and 16 is 41. 41 and 64 is 105. So the normal version of that length vector would be 5 over root 105, 4 over root 105, and then -8 over root 105. So now these guys are still orthogonal to each other because, you know, their unit vectors and the original vector are in the same direction, and so normalize them both, and then you'll still have two vectors that are perpendicular to each other. Now, if you have more than two vectors and you want to find three vectors that are orthogonal to each other, you simply follow along the same, and we'll utilize the next formula in finding three orthogonal vectors, but the process just builds off each other. A set is called orthonormal if it is an orthogonal set of unit vectors. So if we have a set of vectors and we know that they're orthogonal, and remember that means that u sub I times u sub j, or their inner product, is equal to 0 for each of the pair of vectors. And again, if each of them are unit vectors, then what we have is that they are orthonormal. So, like for example, let's just recall this. If we're wanting to normalize a vector, that means that we want to make its length equal to 1. Alright, so let's say we have 1/3, 2/3, 0 as a vector. This one obviously does not have length equal to 1, but to do that we're going to find the length. let's say this is u, and so we'll say the length of u is equal to the square root of 1/3 squared plus 2/3 squared plus 0 squared, and we get the square root of 1/9 plus 4/9, so that's the square root of 5/9. And then to normalize u, we're just looking for a unit vector in the same direction, and we would say that is equal to the square root of 9 over the square root of 5 times the vector 3 over the square root of 5 times u, and so that gives us 1 over the square root of 5, 2 over the square root of 5, and then 0. And now if we find the length of this vector, it is equal to 1 times